So I can write on the screen. Okay, so let's get started with today's class. So in the previous class, we learned about the immediate operand. Okay, so actually we learned about some add and then add I. So usually if I is used as the postfix of the main instruction like add, then we can know that this is the immediate instruction. So which means that this type of instructions use immediate values. Okay. So what is the immediate value? It's small constant number. So and then why we use? So as I explained, so actually think like the normal add instruction. Add instruction requires 3 register operands like x1, x2, and x3, right? So normal add instruction uses 2 source registers. So which means that in order to calculate the a equal a plus 1, then we need to store some values of a in the register x2 and then 1 in the x3. So the problem is that it wastes the register space. And then we also learned that registers are very small memory, it's a very small, it's a fast memory, and then it's very precious. So precious means that because there are a small number of registers, and then compilers need to assign the small number of registers to instructions. So this means that the registers are very precious memory space. So, but very small number like the immediate constant. I mean, the very small constant number can be included in the instruction, like this number 4. So we use the immediate number if some operations use the small constant number, such as the a equal a plus 1. Then this type of instructions can be compiled into the immediate instruction. Okay, so by using immediate instructions, we can save some register space, and then the saved register spaces can be used by other instructions. Okay, and then just remember that this immediate number is the signed number. Okay, it's a signed number, which means that the MSB, the most significant bit of immediate value is the signed bit. Okay, we briefly learned about the unsigned number and signed number here, because actually the immediate number use the signed data type. Okay, and then we learn how to represent this assembly instructions into machine code. Okay, and then I mentioned that computer processor is the digital system. So and then digital systems can only understand binary code like 0 and 1. So which means that our assembly instruction, actually RISC-V assembly instruction, need to be translated into machine code. So there are several types of encoding rules, which encode the assembly instruction, RISC-V assembly instruction into machine code. So this is called the encoding. So, and there are several encoding rules, but as you can see, these rules have regularity, which means that this part is used as the opcode field, and then this part, this field, is used as RD usually. So actually, you can find that for the S-type form, S-type instruction, the RD field is used as the raw part of immediate value, right? Because S type does not require destination register like the SW. So store word. As I mentioned in the memory instruction, the store word does not require destination register, right? Store word requires two source registers. Okay. And then as you can see, this field is used as the RS1 for the R type, I type, and S type instruction. Okay. So we learned about the several encoding rules of the RISC-V instructions, and we will see the detailed encoding rule with the example. So this is the R format instruction. Okay, which means that I close the this one. Yes. Sorry about that. There's it's here. So okay, so I show this table very frequently to you. So you can find the format of the instruction here, right? So you can find the archive instruction here. There's a add instruction, and the sub instructions are also archive instructions. So archive instructions follow the same encoding rule. I put this line. Okay. So if we see the R format instruction, so we know that all these lower 7 bits are used as the OP code field. And then I also explained how OP code field and the function 3 field and the function 7 fields are decided for add instruction, right? So you can find the this instruction table, like add instruction here. Then you can find the add instruction is the R type instruction. So if we know, add instruction is the R type instruction, then we can know that how RD, RS1, and RS2 are represented in machine code, right? Because this is the R type instruction. So we can, if we see the this encoding rule, we can know that RD is here. So if RD means that it's the register number of the destination register, and then RS1 is here, and RS2 is here. Then, now to represent the add instruction, then we need to also fill this OP code function 3 and then function 7 field, right? So how? If you see this instruction table, then you can find that here OP code field, function 3 field, and then function 7 field here. So, to represent add, where the OP code field is here, and then function 3 here, and then function 7 field is here. Also, I kindly color the different instruction. The instruction group has the different colors like here. So you can, if you see this table, I believe you can understand some encoding rule of the RISC-V instructions. Okay. So, and then it's very simple. And then with this table, we can know which values are required for OP code function 3 and the function 7 field for adding instruction. Then we can just fill the number, fill the numbers into the corresponding field. Okay, so for example, this is the add X9, X20, X21. So this is the RD, the destination register. Then this is RS1, this is RS2. So because the destination register number is 9, then we can know that RD field is the 9. So we can fill RD as 9, then RS1 is the 20. The 20 is here, and 21 is here. And then for the OP code for add, the OP code for add is the 011 0011. So you can find the OP code in the instruction table. So you can find the function 3 field and then function 7 field of the add instruction. And then this 9, 20, 21, there are decimal numbers. So we need to translate these decimal numbers into binary numbers, right? So as a binary number is here. And then by combining these binary numbers, then we can generate the 32-bit instruction. And then this instruction represents this add x9, x20, x21, right? It's simple, right? So add instruction is represented as like this. So for the machine code, so the add instruction is 000 001. And then with a hexadecimal number, we can represent this add instruction like this. So I also explained that in order to represent the hexadecimal, in order to translate the binary number to hexadecimal numbers, then we can group 4 bits of the binary number, and then we translate these 4-bit binary numbers to hexadecimal number, right? So 0 is 0, and then as you can see, where is the 8? So 1010 is the 8, actually it's 10 in decimal number. Okay. Actually, so if you know some encoding rules of the RISC-V, then you can easily translate the assembly instructions, RISC-V assembly instructions into machine code. And then actually in the real computer system, the assembly instruction is also assembly is a kind of programming language, okay? And then so it's not high level language like C or Python, but assembly language is also a kind of programming language. So actually in the computer system, this data is stored. Like so in assembly code we see the add x9, x20, x21, but this assembly instruction is mapped to this machine code one to one. Is that okay? So actually in a computer system, this data is stored. Okay, computer can only understand binary code. Then let's see the other format, like I format.
OP 코드랑 펑션에 있는 숫자들은 그냥 약속입니다.
Yeah. So he asked that how the OP code and then I function 3 or function 7 are determined. So it's just there's no rule. So it's just the promise, it's a protocol. Okay. So when the RISC-V is designed, so it's like, for the add, so we actually, there are some rules, as you can see. Actually, if you see the OP code field, you can find that for this category, load has the same OP code field, like 00011. So there are some rules, but if these rules are decided, then you can use it. It's just a promise, okay? And then also you can find that for the store has the different OP code field like here. And then for this alpha instruction, for the shift, arithmetic, then logical and comparing instruction. The alpha instructions use this OP code. And then if we use I-type instruction for shift, arithmetic, logical, and compare instruction, and then we use the OP code like this. Okay. So first, so it's a rule. Okay. So it's when the RISC-V instructions are designed, and then a computer architect, instruction set architect decide how instructions are represented using OP code field and function 3 and then function 7. So firstly, with the OP code, we just classify the category of instruction, right? First, okay. So you can find, oh, this color is mapped to this OP code. Then also you can find that, oh, this color is mapped to this OP code. And then inside of the same category of instruction, then we also need to represent the different instructions, such as the add, sub, and then also exclusive or. Okay, it's the same type of instruction, other instruction. And so we use function 3 and then function 7 field to classify different instructions in the same category of instruction. Okay. So this is also encoding group, and then this is just the promise. Okay. So okay.
타입이 얘 7제곱개가 안 되는 것 같은데 이제 오피 코드를 신빈트는
Yeah, that's very good question. So with the here as the the OP code has the 7 bits, so which means that we can represent the 128 different categories, right? It's a 7 bit. But we just in this table, we have just several types, several categories, like the load, store, and the R type and I type, then branch instruction, like SB type. Then why RISC-V requires 7 bit of OP code field. So in the first day, actually when I introduced about the RISC-V instruction, actually the RISC-V instructions have many extensions, right? Like the multiply or divide also. Actually, this table shows the only integer type based instruction. So actually, if we use some other extensions of RISC-V instruction, then there are many more. There are many other instructions. And then in order to represent these other instruction types or other instruction categories, we use this OP code field also. Okay. Okay. So actually, the size of this 5 instruction is the 32 bit, which means that we can represent the 2 to 32 different instructions. But it's very large. We cannot represent the full different instructions. Okay, let's see the I format instruction. So I format instruction use the 12 bit of immediate field. And then as you can see, I format instructions do not require RISC-V. Actually, so these type of instructions use the immediate field as the second truth operand of an instruction. Right? So only this field is different compared to the R type instruction. So which means that only this part is changed to the immediate value. So that's very simple. I already explained that the immediate instruction, immediate value is the signed number. And the size of this immediate value is 12 bit. Okay. So which means that if we can represent the constant number using 12 bit signed number, then we can use immediate instruction. Then so what is the maximum number for this immediate field? Maximum positive. It's the 2 to 11 minus 1. It's about 2047, right? Okay. So with the immediate number, we cannot represent like the A equal A plus 2048. Right? So actually, I said that with the immediate field, like 12 bit immediate field, we can only represent the maximum number, but the maximum positive number for this immediate field is the 2047. But if we use the statement like A equal A plus 2048, this statement cannot be represented using immediate instruction, right? So it's a hardware. So immediate field has the limited size, and then if the constant number exceeds this limitation of the immediate field, then we cannot use immediate instruction. But if we use the two star like 2047, then we can use immediate instruction like the how can you represent like this? So okay. H at x1, and 2047. And the 2047 is actually 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, right? It's a 12 bit, right? Okay. So this number is mapped to this immediate field, like the signed number. Like if we use the 2047, it's 0, 1, 1, 1, 1, 1, 1, 1, and then RS1 is 1, and then function 3, and then also function 3, and then OP code field. If we can see the instruction table here, like if we use the add then the function, the OP code field is here, and then function 3 field is here. Okay. And then and then we can fill the function 3 field, and the RD is 1, and the OP code, so we can fill the OP code field. It's just simple. If we just understand how this assembly instructions are encoded in the function code, and then if we see the some encoding rule of some other category of instruction, then I believe you can easily translate the specified assembly instructions into machine code. Okay. And then S format instruction. So S format instruction is a little bit different. So as you can see, so RS1 is here, and then RS2 is here. S format instructions do not require RD. So in this case, we just split the immediate field type. So actually, we like other instruction, SB time instructions also use a 12-bit signed immediate number, right? But this immediate field isn't split, like immediate 11 down to 5. It is the 7-bit field, and then the row part immediate 4 down to 0 is this part. So it was already the I type or immediate I type instruction, but SB type does not require RD. So lower part of the immediate number is this part. Then let's see how the SB is encoded. Okay. Sorry. So if you see the reference card, so I need to check the store. So store is the RS1, RS2, and immediate. Okay. So RS1 is here, and RS2 is here. So actually for the store instruction, RS1 is the this part, and then RS2 is the this part. Okay. This field. Okay. Okay, so we learn how to represent the store type as format instruction, and then after that we will learn about the control instruction. And control instruction actually use SB format. SLP format. Okay, but before learning about the control instructions, we will learn how instructions are stored and then how instructions are fetched. So fetch means that actually when we understand some computer system, so we can understand the computer system like this. So this is the processor. You can see. So this is the processor, and then inside of the processor, there is the register 5. And then outside the processor, you can find the main memory. So actually, we use the DRAM as the main memory, and then actually DRAMs are external memory. So it is located outside of CPU. Then how instructions are located here. So in order to execute instructions, then we know that the instructions are given to a processor. So we learned in the first day of the chapter 2 that the processor receives instruction, and processor generates the result of instruction, right? So which means that instructions need to be given to a processor. How instructions are given to a processor? So hint is this. Actually, assembly instructions are encoded into machine code. Like here, we can find that these codes are composed of many bits, right? It's just a bit, so it's a binary code. And then also we can represent any decimal number as binary number, like the 0, 1, 1, 1, 1, 0, 0, 0, 0. Okay, sorry about that. My writing is not good. Also, think like the image data. Actually, it's an image data. Image data is composed of many pixels, and then each pixel has RGB components. And then actually, if we change these RGB values, then we can represent the different colors. So which means that the image, the RGB, also has the binary data, like the 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0. Then why do I show many elements? So normal numbers can be represented as binary numbers. Also, some image data. Some image data can be represented as binary numbers. Also, other data, like your, for example, your text file is stored in the computer, and the data in the text file are also represented using binary numbers. And then it's the same to the instructions. Instructions are also represented using binary numbers. What does that mean? We cannot distinguish instructions and other data. Okay. And then, computer systems, where is data? Memory, right? Data is the memory. Okay. Data is here. So, which means I mentioned that instructions are also same as normal data. So which means instructions are also stored in main memory, right? So this is the stored program computer model. So which means that every data, right? every data is actually stored in the main memory, and then this data include the, like as you can see, program instructions like the machine code, and then also the instructions of another program. Like so, so we just use many other applications or programs in our computer system, right? Like so if we launch the operating system, you can find many processes are running on your computer system. So if you launch a Chrome browser actually generates many processes, which means many applications are running on your computer system. So which means actually programs are launched, and then programs have binary code, and then binary code has instruction. So and then launched means that instructions in a program is loaded into the memory. So which means that the memory has also stored. Memory has also instructions of many other programs. Also, we need to store data in the main memory, right? So think like this. If you watch YouTube video, so in order to watch YouTube video, then you launch internet browser, and then the internet browser connects to YouTube server, and then video. The video files are downloaded from YouTube servers. So which means these downloaded video files are actually data of internet browser. Which means where is this data? This data is also stored in the main memory. So in order to watch your YouTube video, the video data is stored in the main memory, and then this data is moved to a processor. So why do I explain this? I want to explain. In our main memory, we can find also instruction. Then how can we access these instructions? It's very important. So you need to know that you need to know how we can access data in a memory. Address, right? So in order to access data in main memory, we require to know address of target data. So which means, instructions are also stored in the main memory, which means in order to access. So I also explained that instructions need to be given to a processor, which means that instructions are also read from main memory using address of a target instruction, and then if this data is read from the main memory, then this instruction is transferred to a processor, and then processor can read instruction, and then processor execute the read instruction. Okay, understand? So which means that, okay, I will use this. So we know when a program is compiled, some programs have many instructions like instruction 1, instruction 2, instruction 3, instruction 1000, like this. And then these instructions are actually stored in the main memory firstly. And then in order to access, then we need to know the address of the instruction. Okay, address. So, which means when the processor execute an instruction, then using this address, so this is the instruction of address, a processor access the main memory, and then transfer this instruction into a processor's internal memory. Okay, so this memory is called instruction memory actually. So like instruction 1, instruction 2, instruction 3. That's the instruction. Then a processor needs to know the address of this instruction. Also, okay, and then the address of one instruction actually is address of an instruction is called a program counter. It's a code of program counter. It's so much. So in order to execute an instruction, we need to also know the address of an instruction. But actually, this address is handled specially because this is actually the processor needs to fetch instruction from main memory using this address, and then this address of an instruction is called actually program counter, and then usually we use PC because it's a program counter, so we usually use PC for representing the address of an instruction. So it's like this. This is the instruction number 0, and this is the instruction number 1, instruction number 2, and the instruction number 1000. So actually, this instruction number is different from the real address, but then we use the PC like the address of the instruction. Address is 1000. Actually, address is 1004, 1008, like this. So large number. So why do I explain this? A processor using this instruction, and then processor points this instruction in our main memory. Actually, also processor can point the instruction in the instruction memory using this program counter. Okay, pointing is the somewhat important concept in computer system. So if you are familiar with the C, then you can know that C has the pointer. And then I frequently actually the C is very familiar with some system programming. So pointing means that it's just pointing is or a pointer. So pointing means that we know the address of an instruction, and then using this address, then we can recognize the location of an instruction. Okay. So using the program counter, a processor can point the execution. Processor can point an instruction which will be executed, and then if the pointed instruction is fetched in the processor, and then this instruction is executed. Okay, and then also you need to know that a program has many instructions, which means that these many instructions are executed from top to bottom, right? We first, a processor first execute the instruction 1, and then instruction 2, and then instruction 3, and blah, 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 blah. And then I explained that when a processor executes on B instruction, this processor points the instruction. And then processor points the instruction using program counter. It's address of one instruction actually. Okay. So which means that you may remember a special register called PC, right? Where is this PC? Very long ago. Okay. When I explained about the RISC-V registers, I explained about the general purpose registers, right? Do you remember? So actually, the RISC-V instruction use data into general purpose registers as operands. But you can find that there is another special instruction called the PC. Okay, this PC means the program counter of one instruction. Okay, it's actually program counter. So what does that mean? So let's go back to this processor model. A processor has PC register, the program counter register inside of a processor. And then when an instruction is executed, then PC is pointing the instruction which are being executed by a processor. So in this computer model, so this is the PC, and then let us also then the PC of the first instruction is the 1000, right? And then the second is the 1004. Then the third instruction is the 1008. So let us assume that processor fetches the instruction 1 with its address 1000. And then actually the instruction is fetched in the internal memory of the processor. It's the instruction memory. And then a processor wants to execute this instruction, right? So the instruction needs to be given to a processor. How? Processor sets program counter as 1000. That is the address of the first instruction, right? Then with this program counter number, processor access the internal memory, and then with this program counter, so it's the address, because this is also a memory. So this memory is also accessed by address. So PC 1000, then this instruction is read from the internal memory, and then this instruction is given to a processor, right? And then processor completes the execution of this instruction number 1. And then after that, of this processor needs to execute next instruction. How? To say, processor sets program counter as what is next thing? What is the PC of the next instruction? It's 1004. So a processor sets the program counter as 1004, and then this instruction is fetched from the internal memory of the processor with the address 1004. It's a PC. Then processor executes the instruction number 2. After that, change the piece as 1008, then processor can access the instruction number 3. It's already actually usually locates in the internal memory of a processor. Then processor can execute the next instruction. That's how instructions are stored in the memory of a computer system, and how the processor reads instruction inside of a memory using program counter. So which means that program counter is pointing the instruction which are being executed by the processor. Understand? Okay. That's the stored program model. So I want everyone can understand about the PC. Okay, the PC is the address of an instruction, and then when an instruction is, and then this PC is required to read instruction from memory. Because when I first explained about the computer model and instruction in the keyboard, but actually the processor needs to instruction from memory with PC. Okay. Okay. I hope you that's it. I already explained about this, and then okay. So and then I will briefly explain about the logical operation, the RISC-V. So what are logical operations? Actually, every data handled by a computer system is binary data, and the binary data is composed of many bits. So logical operation means that the bits can be manipulated by this type of operation, such as the shift left. The shift left means that the bit location is changed. Like the shift left means that we just shift the bit position to the left, and then shift right is we change the position of every bit of data to the right. And then bit by bit and it's called the bitwise and the bitwise. So bit by bit and means that it's the bit by bit and operation is applied. So if you are doing lab assignment, then you can find the AND module. So AND module receives the 2-bit data, then actually the bitwise and operation applied like the 1 1 is 1, 1 0 is 0, 0 1 is 0, 0 0 is 0. Okay, this is the AND operation. Also, there are other logical operations such as the OR, exclusive or NOT. Also, we can find that these logical operators in the C or Java. So if we use this operator, then this means the shift left operation. And then for the C, we can use the AND operator for the AND operation. And then this AND operator is different from the point operator, right? So it is different, C, like A and B. So this is the bitwise AND operation. And then if we use the MA, so this represents the address of A, the pointer of A. So actually the operator is the same. And C uses the same AND operator, but the meaning is different. So do not be confused. And then for the bitwise OR operation, we use this. How can I call it? Also, this is the exclusive OR, and then the bitwise NOT, and we can use the tilde. And then also, which means that the RISC-V also needs the instruction for this logical operation. So to support the shift left, RISC-V is SLLI, and then SRLI. So this means the shift left, logically shift left logically. So that is called SLL. SRL is the shift right logically. And then for the bitwise AND and the bitwise OR is an exclusive OR, we can use the AND or exclusive OR. For the NOT operation, RISC-V does not support any NOT operation, but we can easily implement NOT operation using exclusive OR, actually. So that's why the RISC-V does not have bitwise NOT operation. Okay. So shift operation use this format here, but so you can also see this table. So you can find that several shift operations here, like SLL, SLLI, SLL, blah blah blah. So you can find that this is the shift amount. Even though the shift operation is the I-type operation, the format of a shift instruction is a little bit different. So it is because shift has the 6-bit immediate number. Okay. It is because actually RV64I handles the 64-bit data, and then RV32I handles the 32-bit data. And then in order to represent the shift operation, then we can set the number of shift immediate data. So which means that in order to shift the 32-bit data, then we can need to shift the 0 to 31 bit. Okay, so which means that we just require only 5 bits. And then for the 64-bit data, we require 6 bits to represent the shift amount, it's the shift numbers. So that's why the shift operations have the somewhat different format. Okay. So if you see the shift instruction, then you can find that even though this is the I-type instruction, you can find that I-type has the 000 function 7 field, right? Also, it is different from the 64-bit shift operation and then 32-bit shift operation. Actually, this format is the 64-bit shift operation. So actually, for the 32-bit shift operation, shift instructions have a function 7 field here, and then actually, as I mentioned, for the 32-bit data, we just require the 5-bit shift amount value. Okay, so this becomes the 5-bit, and then this becomes the 7-bit. Okay, that's how the shift instructions are represented in the RISC-V instruction. And then also, actually, the shift left, so you can find that if you see this shift category, then you can find that shift left has only one type of instruction, like the shift left, and also actually shift has also 2 different instructions, like R-type instructions and the I-type instructions. So, but you can find shift only one type of shift left instruction, like SLL. But if you see the SRL, you can find 2 different types of shift right instruction, like SRL and then SRA. Right? What is different? It's shift SRL is the shift right, and then SRA is the shift right arithmetic. Okay. There are 2 different types of shift instructions. So what is different? So the difference is that if we just shift right logically, like SRL, then which means that we just change the position of bit data. So for example, let us assume that this is the like 1111. So it's a 8-bit data. Sorry, 1111 Okay, this is the 8-bit data. Then we want to shift right by 4-bit, like 4. Then how can you represent the result of this SRL? So this is shifted right by 4-bit, but it is removed because it's shifted right. And then this is changed like the 1111. Then how can you build up this part? The shift RL build up this part using zeros. Then why do we need to have SRA? SRA is different. So for the part 8-bit data, and then if we use the signed number, MSB is the signed bit, right? So 1111 shift to right 4. So if we just perform the shift to right 4 with the SRL, it becomes the 00001111. But if this is the, and if we use the SRA, the SRA consider the MS bit of the target data is the signed bit. So in this case, so it's the same. So this part is shifted by 4-bit, but in this case, SRA detects the signed bit and then fills this part using the signed bit 1111. So if this bit is 0, then SRA fills this field as using zeros. Okay. Why this is important? So actually, we frequently use shift operations for divided by power of 2, right? So for example, 16 divided by 4 is the 4. So actually, we can easily represent this operation using shift right operation, right? So you can just shift right by 2-bit. But problem is that if we use the signed number, this one, the 11111111 is actually -1, right? So it's a shift by 4, the -1 divided by 4. So actually this number is 0, but actually after shift right, it becomes the -1 actually. But if we use the SRL for the this assigned number, then the result becomes the 00011111. So which means it's 15. So which means we want performs the -1 divided by 16. It's the shift right by 4-bit. But result becomes the 15. So it is actually wrong result. So actually it's also the wrong result, but usually. But if we use the 11110000, then the result will be correct. Okay. It's another from pitfall of the binary data, but usually we can use the shift right operator for dividing by power of 2. Okay. Okay, also we can apply the bitwise AND operation like this. The bit is the bitwise AND, so which means that we just check the location of each bit and then performs the AND operation for the same position of the bits of the 2 different operands. And then exclude 4.
그러니까 SRA는 MSB로
그렇죠? 네, right. So SRA it is the MSB for the empty part. of the at the shift operation. And then SLL is the only zeros. Okay, that's the difference. The AND operation is a performs the bitwise and OR, bitwise OR, then exclusive OR, performs the bitwise exclusive OR instruction. So you can find the instruction somewhere here, they'll put it here, but actually you can find the more organized data in the this field. Okay. Okay, now let's learn about the instructions for making decisions. So actually, this type of instruction is very important for programming. Why? We frequently use the conditional statement such as the if A is larger than B, and then we state the C equal A minus B, else then C equal A plus B. So we frequently use the if else statement in C or Python. So it's a conditional statement, and then it's very useful. So based on the condition of the variable, then we can perform the different operation, right? We frequently use this type of statement. And then another example is the loop, iterative loop, like the for I is less than 100, I plus plus, and then A I equal B I plus C I. So this is the for iterative loop. So which means that for this statement is repeatedly executed. Then how can we represent this type of instruction? Is the conditional statement using RISC-V assembly instruction. So think like this. Actually, with the high-level language programming, with the high-level programming language, and we can easily represent the conditional statement. It's very easy, right? But how can we represent the conditional statement with assembly instruction? So I already explained that a computer executes many instructions. Instructions are executed from top to bottom. Instruction 1, I2, I3, blah, blah, blah. So instructions are executed from top to bottom. Then how can we translate this statement using assembly code? So for this statement, if we see this statement, so we can find that we need to perform this if statement, but actually we need to compare the A and B, the magnitude of A and B, and then based on this comparison result, then we need to perform the if statement. And then based on this result, we execute the different instruction like A minus B or A plus B. But when this instruction is translated, which means compiled, assembly code need to have both instructions, right? Instructions are just data. And then we don't know which instructions will be executed. It is determined in runtime. Okay, we don't know. So which means that assembly code, like assembly code, need to have both instructions. Like, oh, we need to have sub, we need to have and based on this result, a processor can execute sum, or a processor can execute add instruction, right? And then I explained that when a processor executes a certain instruction, the processor points the instruction using program counter. Okay, so what does that mean? When a processor executes sub instruction, then PC, the program counter register of a processor, the program counter is set for this sub instruction. Or if a processor needs to execute add instruction, then a processor needs to set program counter as the PC, the address of add instruction. You understand? So, which means that in order to support conditional statement, processor need to have instructions that can change program counter. Okay, which is a conditional statement. The processor needs instructions that can change program counter inside of a processor. Right. Understand? So based on this change in the PC value, then if the process PC is pointing the sub instruction, then processor can execute the sub here. Or based on the result here, then PC needs to change it to the program counter value of add instruction, then a processor can execute add instruction. Okay, you understand? Because a processor use program counter for pointing the instruction which are being executed, then in order to implement the conditional statement like if else, then processor needs the instruction that can change PC. And then because this statement is compiled. This statement has the instructions for sub, instructions for add. Okay, we assembly needs to have both instructions, and then based on this result, the PC is changed into the sub instruction or add instruction. Also, another example is the iterative loop. So, iterative loop means that when this instruction, this statement is compiled, this statement requires this I, control for I, but we know that this statement is repeatedly executed. So this is the add instruction, right? So just add x1, x2, x3. So this is add instruction. And actually, if you see this iterative loop, based on the result of I, variable I, processor execute the same instruction, the add instruction, repeatedly. So which means that based on the result of I, a processor set the PC for this add instruction, or if the I becomes the 100, or if I is bigger than 100, then you know, so this program execute the very next statement, right? So which means that after this add instruction, we can find some next instruction. So which means based on this I, the value of I, the PC of a processor can be set for the add instruction, or PC can be set for the very next instruction. Okay, that's why we process the Python instruction that can change program counter. Okay, so that's why you need to also understand how the PCs are used to process it. So this type of instructions are control instructions or branch instructions. Because why do you call it a branch? Because if you see that this conditional statement based on the result, then we can execute this part like A minus B, or we can execute the A plus B. So which means that the program execution paths are divided into two parts. So it looks like a branch of a tree. So that's why this instruction is called branch instruction. So also, this branch instruction check the condition of some variables. So this type of branch instruction is called the conditional branch instruction. Okay. So RISC-V has the several branch instructions. Like in this instruction, the first B represents the branch, obviously, and then the next two letters represent the condition of a branch instruction. So this instruction is the BEQ, so which means EQ means the equality. So, and then also you can find that this is the RS1, the source register number 1, and source register number 2. So if you see that this example, so you can, oh, this is the branch instruction B, and then the condition is we need to check the equality of what? RS1 and RS2. So which means we just check the values of RS1 and RS2 and then check the equality. And then if this condition becomes true, right? If these two registers are equal, then what is this one? L1. L1 is it's a label. Actually, by this number, branch instruction change the PC of a processor. Okay, so by changing the PC, then we can change the next instruction of this branch instruction. Okay, so if you see the B and E, the first B represents the branch, and E is the not equal. So it just check this one. It's to check it's not, if RS1 and RS2 are not equal, then it becomes true. Okay. And then also you can find some other branch instructions here. Okay, so the branches you can find the BQ, BNE, BLT, BGE. So you can find the meaning of the branch instruction here. The equal, not equal, the less than, and T. G means the great or equal. Okay. So branch instruction start with the B, and then also you can find the condition of branch. So please understand how the branch instructions are executed in the process. Also, I want everyone can understand how a processor executes a certain instruction. The processor points instruction which will be executed using program counter. And then by changing the program counter, the processor can select the execution which will be executed. Okay, the instructions which will be executed. Okay. So in the next class, we also learn about the branch instruction. It's a very important part in this chapter. And so I want to cover about some procedure. That's actually the function. Okay. Thank you for your attention. Any questions? Okay. 네. 없어졌는데, 어드레스에서 이제 계산됐듯이, 아까 옛날에 통월드 할 때, 뭐, 옵셋 하고 이렇게 했잖아요. 그 옵셋 파트가 이미디어트 밸류가 있습니다. 네. 네, 그러니까 그 베이스 어드레스의 값, 그다음은 레지스터에 저장되어 있는 어드레스 값 플러스 이미디어트 밸류. Thank you for your attention. See you in the next class.